Okay, fine.
ಕೇಳಿಸ್ತಿದ್ಯಾ ಸರ್ ನಾವು ಮಾತಾಡ್ತಾ ಇರೋದು? ಮೇಡಮ್ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡಿ. Just a minute, ma'am. Introduce yourself.
Madam. Okay, I'll take over. I welcome Madam Nirmala to this session. She'll be handling Metso DNA hardware.
But I can't hear anything.
Modules. I think
Excuse me.
Yes.
Hello?
Tell me.
I can't hear anything here.
You're not able to hear anything.
Madam, 2 minutes.
Okay.
I will not be able to hear. I'm not able to hear. Yes, see, because I can only hear from that PC. I can't hear.
ಸರ್ ಮಾತಾಡಿ ಸರ್.
Madam.
Hello. Can you hear Swati?
Ali, unmute Swati.
Hello.
Swati. Faculty PC ನನ್ನ unmute ಮಾಡಿ.
ಒಂದು ನಿಮಿಷ. ಸ್ಪೀಕರ್ ವರ್ಕ್ ಆಗ್ತಿಲ್ಲ ಸರ್ ಇಲ್ಲಿ. ಇವಾಗ ವರ್ಕ್ ಆಗ್ತಿಲ್ರಿ. ಬರ್ತಾ ಇದೆ, ನೀವು ಮಾತಾಡೋದು ನಮಗೆ ಕೇಳ್ತಾ ಇದೆ. ಅಲ್ಲಿ ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿದ್ದೀರಾ? ಹೌದು, ನೀವು ಮಾತಾಡೋದು ನಮಗೆ ಕೇಳ್ತಾ ಇದೆ.
Nirmala madam is unmuted already.
ಅನ್ಮ್ಯೂಟ್ ಮಾಡಿದಿರಂತ.
Okay.
Okay, madam.
Nirmala madam, you are able to hear me? Padma here.
Yeah, I can hear you now.
Okay. Now I think we can start the session. Are you comfortable?
Yeah. That's
okay. Okay. I welcome Madam Nirmala to this Metso DNA hardware, ACNCS and digital module session, which is very, very important. As we all know, ACNCS is the heart of this Metso DNA system. Actually, BHL went into the collaboration with Metso DNA Finland in the year 2009 and 10 around. And since then, she's involved in the indigenization of lot of digital modules and ACNCS. So she'll be the faculty today, and she's got a profound knowledge of designing these digital cards. So we may avail her knowledge in using in our sites and all that. So lot of our site peers will be associated directly with handling the modules and other things. So whatever problems you have come across in while commissioning or while handling the plant maintenance, etc., can be sorted out as of now. And she's got a very vast experience in handling the cards and in-depth design she's involved in. So let us make use of her knowledge for next 1.5 hours. So, Madam Nirmala, over to you, please take over.
Good afternoon. Padma, am I audible? Yeah? Okay.
Yes, you are very much. You may go ahead. And there is one instruction to all the participants. Just before leaving, after every session, enter your feedbacks. The format for feedback entering is also given in the chat box. So kindly follow the format and enter your feedbacks. This is very valuable to us. And kindly mute yourselves. There is a lot of noise interference sometimes. So let us all keep in mute mode and listen as much as possible and gain the knowledge. Thank you all. Over to Nirmala madam, please.
Okay, so good afternoon. So today I'll be covering the modules used in Valmet DNA. So the modules which are there are going to be divided into 2 sessions. So I'll be covering the digital modules, while in the second half you will be having the analog modules. And see, in this session we'll be only covering the hardware, because I've been involved in the hardware of the modules, and I've been involved in the indigenization of these Valmet DNA modules. So to start, before going directly into any of the digital cards, I'll just give the structure of this IO group. I think most of you will already be familiar with, but just covering it. So normally in an IO group, you're going to have you're basically going to have one power supply module which supplies a power supply for the rack. Then you have an IBC module which is a bus controller and takes data from all the IO cards in this IO group, and also gives data to the IO cards both ways. It controls the IO group, and you are going to have around 16 modules in one IO rack. So this is another view of the same thing. So here you have your power supply card, you have your bus controller, and you have one mounting base on which your power supply card and your bus controller is that is IBC module is mounted. And you also have one more mounting base here. This is used for mounting the IO cards. Now this mounting board can be used for mounting about 8 modules, 8 IO modules, and the field connection is all taken from the front. The connections given to any slot on this mounting board. This is this. See, if you go by the BHL number, it is called 69235 MB51A. But referring to the collaborator number, it will be MBI8. I think, okay, let me first, I think as you all know, BHL has entered into a collaboration with Valmet DNA, and we have got the design from Valmet DNA. In the case of this modules, there has been no design which has been done for these modules. That is not for the IO cards and power supply or controller card. The design is as such as obtained from our collaborator Valmet. Now again, coming back to this IO card, I just wanted to that there are some 8 modules on one mounting base, and on each slot, the connections to each slot is identical. This means that any module can be mounted in any slot. There is no restriction, that is, they can be interchangeably mounted. And all these modules are also very small and compact. As most of the modules have a PCB inside, and they are mounted in a plastic enclosure. The next thing you can say is yeah.
Mute all. You are having rights now to mute all. So kindly give mute all so that no noise interference will be there because lot of background noise is there.
Okay, it's given. Okay.
You are having host rights now. You mute all. Nirmala madam.
Thank you. No, I don't take it. Sure. Yeah, Padma. So I'll continue. Okay.
Yes, you please continue.
Yeah. So, well, as I was telling that there are 8 models which you can mount on one mounting base. And in this mounting base, you have 2 connectors which connect to the mounting base on which the IPSP and bus controller are mounted. So now these 2 connectors take the signals from the mounting base on which the power supply and bus controller are mounted, and they convey it along to this end. And another mounting base, that is MBI8, can be serially plugged in on the other end. Since all the connections which enter the module are also brought out to the other end of the module. It is just routed right through. And the next thing about these modules are they are all hot swappable, which means the modules can be plugged in at any time of the operation. That is when the power supply is on itself, it can be interchanged. Okay, this is another view of the mounting base which is used for mounting the IO cards. So you can see this will be the slot, and with these 2 connectors, each IO card gets plugged into your mounting base. The connectors which on the side there are 2 more connectors which get connected to the mounting base on which the power supply and the IBC are mounted. And these signals are routed, the same signals are routed to every connector. and they are also brought out in this end so that the next MBI8 can be serially connected to this. Okay, this is showing basically all the IO cards which are available in Valmet DNA. So here we have the analog group, which is the analog input modules. These are the analog input modules and 2 analog output modules. Here are the 4-channel analog outputs and the analog inputs. This will be covered in the afternoon. Then we're having the digital cards, which will be covered right now. So we have your 24 volt and 48 volt input module. Out of this, the commonly used module is the 24 volt, that is DI8P24. DI8P48 version is also not used commonly, but I'll be just covering it just to tell, just a brief description of what happens in the 48 volt. Then we also have this DI4U120 and DI4U240, and this is a 4-channel digital input card. It takes inputs for 120 or 240 volt VAC. This card is also not used very commonly. Then we have another card which is eight digital input cards, that is DI8U120 and DI8U240. Here this takes 120 or 240 volt VAC. And see this set of cards, that is all these ones which use 120 and 240 are not commonly used. The commonly used one is this 24 volt input card, as well as this 4-channel output card and this 8-channel digital output card. So these are the commonly used ones, but I'll just touch upon all these cards just for completeness. Your DOI4RO is a 4-channel digital output card, and the 8RO is a 8-channel digital output card. Then you also have the IBC and the IPSP. So this will also be covered in the afternoon. That is, this whole set will be covered in the afternoon. And now from this slot here, we have the frequency input card, and then we have frequency input card, which I'll cover this. And then you also have the 3-wire and 4-wire RTD modules, and the TC8, that is the thermocouple module, 8-channel thermocouple module. Now the RTD modules and the thermocouple module also will be covered in the afternoon, being analog cards. I'll just start off with the digital output card. This is a 4-channel card. The BHL number is 69235DO51A, and the collaborator number is DOI4RO. So you have on the module, you have the number here written DOI4RO, and the BHL number gets written on this portion here on a label. So now this digital output module has 4 channels. They're potential free electromechanical relay output, and they are normally open contacts. Now one thing about this, each IO card communicates with the IBC over a serial bus. That is, there are in fact 2 serial buses running between the IBC and the IO cards. Now the communication from all modules are almost identical. So I'll just go in detail with this digital output card, which will also be the same for the other output for the other cards. That is, communication between the IO card and the bus controller cards. And when you come basically to the structure of any of these IO cards, they are all they are very compact and very small and very easy to handle. Some of these modules have a single PCB, while some of the modules have 2 PCBs inside, and the 2 PCBs are connected between each with two PCBs are connected by connectors. They are just plugged in connectors and they are pushed inside the same enclosure. But whether it's one PCB, whether the module has a single PCB or two PCBs, the size of the module is the same because that enables the interchanging also. The normal size of a PCB is 120 mm by 80 mm. And the module dimension is 130 mm by 24 by 95. That is mm. 130 mm by 24 mm by 95 mm. That's how compact the module is. And one thing about all these cards is that we do not have any hardware jumper settings or any other switches to be set on the module. We have a switch only which is there on the mounting base, that is MBI8 for the IO cards. There are no other switches or jumpers in any of the cards. There's no selection to be done on it. So now when I go inside the module, so this is kind of a block diagram of what is available inside the digital output module. See this portion, that is the portion, this is the system side portion. This portion communicates with the IBC module over the serial bus. Now this portion remains same almost for all the modules. It is only the field side which varies depending on the type of the module. Okay. So this is a microcontroller based module. You have the microcontroller used here is a 8089C51RB2, and then you have all its corresponding interfaces also. So one of the interface here, the first interface which I'll be talking about is RS485. See now this is the serial bus connection which runs between the IO card and your IBC, along which data is exchanged between the two card modules. Now this RS485 is connections come onto this X1 connector. So this basically is the system that is has all the supply voltage and all that which is used for powering up this logic side, which is separate from the field side. Because there is an isolation between your logic side and your field side, or what you can call is the system side. So here you have the microcontroller which communicates via RS485 to the IBC. So these connections run on your X1 connector. Additionally, you also have the microcontroller which controls the LEDs. The number of LEDs on every module varies. Now in this case, since the channels are phone, we have 4 LEDs here. The microcontroller controls these LEDs. It basically writes onto one an IC, buffer IC, and then from the buffer IC it gets the LEDs are controlled depending on the input which is written. In this case, depending on what is written from the IBC side. We also have a watchdog timer. The main function of the watchdog timer is that it provides a reset to the CPU at the beginning. So this enables all the voltage levels to reach a proper level before activating the program and everything. So everything starts on properly. Normally the reset signal is active for around about 140 milliseconds after the 5-volt supply has reached its 4.63 volt supply. So this is the watchdog timer, watchdog circuit which is associated with which the microcontroller controls. The next thing which we have is the card address. So now the card address, it's basically because the module needs to know when the IBC is calling it. When the IBC addresses it, the appropriate module needs to respond. This is known only by the address on which the address and the location in which the IO card is mounted. So for this I need to go back to the coming back. So the addresses basically come from this mounting base. As I have told you earlier also, this mounting base, both the mounting base in which IBC is mounted gets connected to the mounting base in which the IO cards are mounted via these two connectors. Additionally, there's also one rotary switch over here. So now this rotary switch can be adjusted. So normally the MBI8, which is next to the mounting base on which IBC and IPSP is mounted, is set to 0. Now there are 4 signals which come from this switch, which get connected to each of the slots. So these 4 signals form part of the address lines, which helps in enabling the selection of the IO card, on which so this selection, that is that one, these four ones indicate on which mounting base the IO card is mounted. So the mounting base, that is MBI8, which is close to the MBM 120, is normally set with 0. Is set with the address 0, while the next MBI8, which is further away from the mounting base, that is normally set with the address 4. What I'm saying is this first one is set with the address 0, while the second one is set with the address 4. Now these four now from these 4 switches, there are 4 lines which go to a slot, and additionally in every slot there are 3 more signals also. Okay, these these signals come from the mounting base, and using these 3 signals, any one of these 8 slots can be addressed, that can be selected. That's because you just use a binary. Using 3 lines, you can select 8 cards. Like the first one is 000, next one is 001, and so on and so forth until the last one where you get all 3 ones, and you can and using 3 lines, you can address these 8 slots. So a combination of what is there from the switch as well as the individual slot. So you have totally of 7 address lines, that is 4 from the switch and 3 from the individual slot, which enters into every IO card. And this together gives the address of the IO card. Okay. About the watch. Okay, I think I see a question that you want the watchdog timer to be told again, right? See, this is the watchdog timer is just used when that is when you plug in your module. Okay, and see, when the module is just plug in, we are putting all the circuitry on a reset, so that you're going to let all the voltages to settle down. So that reset signal will be given for 140 milliseconds. So once it is just so that you do not just immediately allow everything to start working. You just keep everything on reset, give some time to settle, and then the reset is released so that the module starts working properly. So that is a function of the watchdog timer, and that's basically an IC which on power on always generates a reset, which keeps the microcontroller also under reset and then releases the reset, and the microcontroller starts working. So I hope that is okay. It's answered your question. So now from here, what I have told is coming back to this address, we have 4 lines which are coming from the 4 lines which come from the rotary switch and 3 lines which come from every slot. So you have a total of 7 address lines which enter into the module. So these address lines also enter the module via this X1 connector. Okay. So now depending on, and when the CPU reads this, that is the microcontroller on the IO card, reads these oh. Excuse me, how do I enlarge this? It says there's a request for enlarging the image. This is the maximum, no? I have Can I enlarge the image? This is maximum.
Yeah.
But I will not be able to see the chat. That's all. Okay, that's a problem. Then I have to switch off the chat. I'll see it.
No, actually, they have to display their things. No, they have to change themselves.
Okay. So, okay, coming back to so we have a total of 7 address lines which come in through this X1 connector. And when the microcontroller reads this address lines, it will be able to identify in which slot it is, because the 3 lines will give you the slot number. And when the IBC wants to address any of the microcontroller, any of the IO cards, when the IBC wants to address any of the IO cards, that will also be able to figure out, because the first one will be 0, it will be slot 0, and the next one will go on to address 1, 2, 3, 4, and until 7. And one more thing, the addresses of this is derived by, you take the rotary switch multiplied by 2 plus the slot number. So that will be the formula which is used for arriving at the address. So in the first case, since we are making the rotary switch as 0, so we have 0 into 2, which is 0, plus the remaining is you get directly the slot number, which will be running from 0 to 7. Now the next number, if you go to the second MBI, it will become 8. Since we are setting the selector switch to 4, so the address of the first slot on the second MBI becomes 8, because it is 4 into 2 plus 0. So that becomes the 8th IO card. And so on we can get until the 15th IO card. So this is how the IBC can read all the 16 IO cards. So the first one is between 0 to 7, which is in the first MBI8 lot. And the second is between 8 and 15, which is mounted on the second MBI8. So this card address also is read in by the CPU. The seven addresses which are read into the CPU. The lines which enter are in parallel. That is all the 7 lines together enter into X1. But because the CPU has a limited number of pins, these seven lines are run through a parallel to serial converter, and they enter the CPU serially. The CPU reads these addresses only in the beginning. It keeps reading it repeatedly until it gets the same result for 3 successive times. And then once this is obtained, once the address is obtained for 3 successive times, the address is locked, and that address is used until the next reset is given to the module. So this is about the card address. We have another portion also, which is called the product ID. So now this product ID basically comes as when you have the same kind of PCB which is used for 2 types of modules. It gives an idea for the CPU as to what type of module it is. Like examples for where the same PCB are used are like you have your 3-wire and 4-wire RTD cards. You have the same PCB used, but the components mounted on them are different. So in that case, the CPU, by reading the product ID, this product ID is available on the PCB only. These 4 lines are read in, and this gives an identification, and each depending on what is up, that is, they can either be pulled up or down. And when the CPU reads it, it's able to identify what is the type of model it is. Now in this case for DOI4RO, the PCB is unique, and this module has only a single PCB. Okay, and the PCB is a 4-layer PCB. It has SMD components. It has components mounted on both sides, and so here there may not be much current, but anyway, all the cards have this product ID to help the CPU to identify which is the module. Then you also have your digital interface. This digital interface is basically for communicating. That is, there is always isolation between your field side and your logic side. So in this case, this is a purely digital card. So the signals which come from your logic side gets opto-isolated and then is sent to your fields. So that interface is the digital interface. So coming to the connectors which are there on the module, you have basically in this case you have three connectors. One is this X1 connector, which I have all the system side, that is all the logic side signals coming in. Then you have the X2 connector, which is the field side. It could be the field side power. See here there are two. Some of the modules get powered from the 24 volt, which comes from the mounting base. The mounting base, that is MBM 120. Now MBM 120 is a mounting base on which IPSP and the power supply cards are mounted. So for some of the modules, they get the power supply from that mounting base, and that comes in through the X2 connector. Some other modules like the digital input card gets its field supply from the connector which is connected to the MBI8 module. Now this I will cover when I come to DI8. So there both these voltages come onto the X2 connector, and this X2 connector basically powers the field side of the of any of these modules. Now X3 connector is the connector which you see in the front plate and the front side of the module. That is this connector. This is the field connector through which the field connections are taken. And then here you have your four yellow LEDs also. So now when you come, so the early slide covers basically what is the logic portion of this, of the IO card. Now when you come, what is specific to this digital output card? So now the digital output card is basically here you get the signals which control the digital output card on the field side basically has four relays. Since there are four channels. And now each of the channel is isolated between each other also. And there is also isolation between the field and the logic side. So the isolation between the field and logic side is achieved using an optocoupler. So the signals from the microcontroller are written onto a buffer, and from the buffer they go on to the okay. So from the microcontroller, they get written onto your buffer, and from the buffer, they get written onto an optocoupler. And from the optocoupler, the signal comes here to the relay. This is the coil of the relay, which is of a single channel. And it activates the relay depending on what is the value written from the microcontroller, which in turn gets from the IBC. So you have the value written from the IBC because it's output card. The value has to come from there, which gets written onto the digital output card, and in turn it gets opto-isolated, and the signal reaches the coil of your relay, and then this gets into your contact. Now here for every channel you have a separate NO and COM. That is your common, and your common is separate. So every channel has a different COM point. It is not common across the channel. So every channel will have two points. So that's why you are having only four channels, and though the field connector is going to have eight points. That is, you're going to have eight signals coming out in your field controller, two for every channel. So the first one, normally the one closest to the LED we name it as the channel 0, and you go on to channel 1, 2 and 3. So this is a very simple model. This is just you have. Key thing is here you have isolation between from channel to channel also, and isolation between the field side and your logic side. So both are achieved in this model. This is the same thing which I told earlier, that for every channel you're going to have both the signals. This is the signals which you get on your I/O connector on your on the field side. So you have one normally open contact and your common contact. This is for the first channel. These two pins go on for the second channel, third channel, and your fourth channel. And you have one LED which whenever one is written onto it, the corresponding channel glows. Yeah, here I'm coming on, as I told earlier itself, there is isolation between your logic side and your field side. See, the isolation between your logic side here is around 1500 VAC for 60 seconds, while that is between logic and your field. You also have an channel to channel isolation for your digital output card. In this case, it is 2200 VAC for 60 seconds. That is between each channel. Yeah, I just saw your question saying that if the LED is continuously blinking, what will be the status? So when all the signals are continuously blinking, it means that the connection between your module and your process controller is broken. There's no communication going on between the two. There's no communication going on between the two. Otherwise, now in a normal state, the LED will be steady. Then shall I move on to that second? So this is the basic structure of a module. So now shall I move on to the next module? Okay, so this is now the 8-channel digital output card. Now this is also very much identical to your 4-channel one. The working is almost same in every manner. This has 8 channels. It has electromechanical relay output, and they are also normally open contacts. Here, since you are going to have 8 channels, you are also having the number of LEDs have been increased from 4 to 8. And again, you have your field connector here. But here the number of pins on your connector has increased because there are more channels. So same thing is a channel with electromechanical relay output and normally open channel. See, now because you have got 8 channels, what you are losing out here when compared to your 4-channel card is that there is no isolation between channel to channel. Your 4-channel digital output card has isolation, while your 8-channel digital card does not have isolation. Because if you see, the PCB is still the same size. So you are going to mount more relays, and so you're increasing the channels from 4 to 8, but this comes at the cost of your isolation between channels. So in this case, unlike in the other case, you have every signal has a normally open pin, and you have the last 2 pins which are 9 and 10 which are common. And these pins are common for each of the channels. That is, all of them have the same pins. So you get the signal for the first channel between NO and COM, and similarly between NO and this one. Unlike in the previous case where you had a separate COM. And so here there is no isolation, there is no channel to channel isolation. But however, you do have your logic to field side isolation. So in this case, you have a field connector which is going to have your 10 pins. So 8 for the channels and 2 pins for the common. Total of 10 pins are there. It's the same thing. You have only isolation between your logic side and your field side. And here it is 1500 VAC for 60 seconds. That's the isolation between your logic and field side. Which is the same like in the other case. So here you have a more detailed picture. Here, as I told you, there's a microcontroller. Like in the DOFO RO case only, it writes onto an wire, a buffer writes onto your optocoupler, which in turn controls the coil of your relay. And this becomes a circuit for your first channel. But in this case, the common is the same. The same point is rooted in the PCB. It's the same thing, and you have this is a block diagram showing the first channel. You have such eight identical channels. And from here, the field voltage for this one is taken from your mounting base as a 24 volt, from which your field is powered here. So now moving on to your digital input card. So now we have two types of digital input cards. You have your 24 volt input card as well as your 48 volt input card. Now both of these cards are having 8 channels, and they have a 24 volt current limited voltage supply. Okay. So this is a 8 channel digital input card, and you have the 24 volt which has a channel specific 24 volt DC current limited voltage supply, while in the 48 volt digital input card you are going to have a 48 volt voltage supply which is supplied on it. Both of these have 8 channels. Okay, and in this case our collaborator number will be DI8P24 or DI8P48. No, you're asking, okay, coming back to the chat, there's a question saying if one channel fails, will it lead to misbehave of all the other channels? No, not necessarily. Then here, when you're coming back, okay. So now, okay, here you have both your 24 volt and your 48 volt voltages. There are two versions of models. The one which is normally used, the digital input card, is the DI8P24 volts. So now here also your logic side is identical to what you have in your digital output card. But and here again, since you have 8 channels, you have isolation only between your logic and field side. So coming to the block diagram of your digital input card, it's just showing the block diagram of a single channel. Here also you have the microcontroller which writes onto an optocoupler. Isolation between your field side and the logic side is achieved using a optocoupler. And additionally, you have some additional protections which is there for every channel. You have a resettable fuse which is there on every channel. So this protects your voltage supply to see that there is, it protects the voltage supply to the sensors are protected with a resettable fuse. So that is one protection which you have. You also have a an overcurrent monitoring, which monitors if there's any overcurrent in this channel, and it gives a fault to the microcontroller and generates a overcurrent fault. And also the field supply, that is a field supply which is used here, is also being monitored. That is a field power supply is monitored. If it falls below a certain level, a fault is again generated to your microcontroller. So the three things, as I told, are one is overcurrent monitoring, the other one is the field supply monitoring, and then you also have isolation between a field and logic side. Plus you have the voltage, the field, the sensor voltage also being protected by a resettable fuse. So these are the extra protections which are there for your digital input cards. So here the rest is the same. Yeah, that is the rating. The 40 milliamperes is the rating of the module. Okay, only one portion which we need to take care out here is that the digital input card, unlike all the other I/O cards, there are two models. That is the digital input card as well as the frequency input card. They take their field power from the connector which is mounted on the MBI8. Okay, so going back to the MBI8. So the digital input card and the frequency card gets its power supply from this connector which is mounted on the MBI8, while all the other I/O cards get its power supply from the mounting base. So that is sent via this connector it goes on, but the digital input and frequency card gets whatever voltage you are applying here. Now, so when you are having a 24 volt digital input card, you have to plug in, you have to give in 24 volts here at this point. But however, you cannot mount again you cannot mount a 48 volt digital input card because this signal is again in turn passed through all the slots and they also go on to the next MPI, which means this whole rack, once you put a once you supply a 24 volt here, all the cards get the 24 volt in the appropriate point. So you cannot mix a 24 volt digital input card along with a 48 volt input card. So basically the 48 input card should not be mounted along with the 24 volt digital input card or the frequency input card. So both these cases, care should be taken. So you cannot mix the power supply. And anyway, the plus 5 volt which powers the CPU and other related logic is got from your mounting base only. Only the field power supply comes from your from the bottom connector. Okay, moving on to the other. These cards are not very. These are never used in fact. But these we have just as 120 volt VAC, 240 volt VAC, and 124 volt DC. These cards also these are four channel cards. Here again you have isolation between the channels. Here this voltage is again stepped down, and like in a digital input card, it is again read in by a microcontroller. And here you have both channel to channel isolation as well as logic to channel isolation, logic to field supply isolation. This is now the 8 channel. Again, these are again 120 volt and 250 volt AC. Here also it's stepped down and used. This card is also not used frequently. It's not used also. But here again, you do not have isolation between the channels. It is coming to the frequency input card. So now this now this frequency input card is used in operations where you need to measure the pulse count or the pulse frequency. Now you have 4 channels here. Uh, you have 4 digital input channels, and you have one separate DI and DO. Now these two, the channel 0 and channel 1 together make a quadrature sensor also, and channel 2 and channel 3 form the other quadrature input. And this DI and DO is not a normal DI and DO, but these are used for controlling your channel 0. So here you have all kinds of pulse modes, like you can start, your start value is 0. It can either count on rising edge, count on all the edges. And in the quadrature road, no, I didn't get, okay, I just got this. With the chat, you asked a question, are DIs and DOs self-powered in some cases? See, DOs is basically just an electromechanical contact. I didn't get your question. And DI, there is a power supply which is provided by the DI card. Since the DO is basically just a contact. So here you have, so here you basically, yeah, here so here this is not an independent digital input card, but these are used for controlling your channel 0. That it could be either the gate signal, channel enable or clear functions. That is for the DI. And DO gives a status, whether the count has crossed a limit which has been set by the card, or what is the, like if it is counting up and if it is increased, it's crossed the higher limit, it might go out. That depends on the setting on which it is done. And the DI could either be used for clearing, which will clear the pulse count, or it could be gate enabled, where the pulse count comes between either your rising edge, between two rising edges or two falling edges, or one rising edge, falling edge, which can be set. Or you have the external enable mode, in which case the pulses are counted whenever this DI input is high or low. That is again set. So this is basically used for counting pulses and the frequencies. So here you have much more complicated LEDs here. Like you have 4 LEDs which give the status of your inputs, and these come whenever you are missed a pulse and it does not come in the time. This LED glows. Then this CO becomes, when you're using a quadrature, it shows whether you're counting up or down. This is for the first pair and your second pair. Here also is the usual thing. If the LEDs are all blinking, it means your communication to the process server is broken. Now coming to the AC and CS. See here we basically deal with only the hardware, and at least okay, our group deals with the hardware. So any of the whatever you're doing any system, this thing will be covered later on in another session. Here I'm just giving a basic idea what is there in an AC and CS module. So the main thing of this AC and CS module, it has no moving part, and it has a compact flash through which you are writing into it. See, actually, the frequency input card has been used, as far as I know, only in one project. So it depends on what they use on the system side. So coming to your AC and CS, I think that question, because I'm from the module side, I know the functions of the module, but when it's done on the system side, I think it's better that you address it for a person who's coming tomorrow from the system side. But then they can at least tell you how exactly they are using the modules in which point they can use the module. Okay, the structure of the ASINs. Okay. I'll go on to this. So ACNCS, the ACNCS structure is much different from the usual IO cards. It's much more bigger. You can consider the ACNCS as a basic. It's almost like a PC. Like it has your hard disk, it has a motherboard. It's much more bigger. The weight is around about 4.5 kgs. The dimensions also the 210 by 87 by 296. It's a fanless construction, and here cooling is by heat pipe, and it has a very massive heat sink at the back. So where all the heat is taken from the controller and it is connected to your heat sink and heat sink at the back. This could be either wall mounted or it could be mounted horizontally. In our case, it's always mounted horizontally. It's just placed like that. So here you have your you have some PCI slots, and okay, the memory inside the ASNCS is a 1 GB DDR2 with 667 megahertz. The processor for ASNCS is Intel Celeron. Then you have a 512 MB compact flash, and the expansion two, that is two slots are provided for expansion for adding any kind of PCI card onto the slot. The operating temperature for this ASNCS is 0 to 50 degrees, while the temperatures minus 20 to 60 degrees. So this is the connections which you can see in the ASNCS. So here you have your compact flash. This is your PCI slot. Then yeah, the ASNCS will basically work on Linux. Then later on here you have your process bus. You have two process bus and your field bus. Then you have your COM port. Then this is okay. This is a VGA port in which you can connect a monitor. Here you have your PS2 port for where you can have your keyboard and mouse. But then this monitor and PS2 port for keyboard and mouse are basically used during testing. So basically, in one ACNCS, you have two process. See, in that there'll basically be a liquid. So what? Sorry, coming back to the question which you saw on the chat just now, that there is a your heat pipe. You basically have a liquid, and as this moves up and down, this cools. It forms vapor, goes to the heat sink, cools, and then it comes down into the comes back again. So it keeps circulating all the time, and that's how the cooling is achieved in the ACNCS. So ACNCS also has an alarm input. The voltage input is 18 to 36 volt, but normally you give it at 24 volt. It has two USB ports and a serial RS-232 port. Yeah, it has a speaker and mic also, but which is not thing. So now in this PCA, you can connect anything. You can extend it either with a Profibus card, or you can have your field foundation field bus. Anything can be put there, or you can extend it again to have your field Ethernet card for having an extra field bus. So now ACNCs you can have a maximum of 3 field buses. Then you can have 2 processor buses, but the total number of field buses get limited to 5 numbers here. Yeah, you have 2 LED cards which are identical because, as I said, there are 2 ways of mounting. You can either do it horizontally or you can do it vertically. So both the information on both the LED cards are identical. You have the power signal which is green. It's when the power supply is switched on. Then you have the run LED which is also green. And then you have another 5 LEDs which out of that PB1 and PB2 is for your process bus, and FB1, FB2 and FB3 are for your field buses. Okay, I think yeah, that's it. Is there any more questions?
Participants may unmute themselves and ask questions, please.
Now, what is the purpose of microcontrollers and DI and DO cards? See, see the micro. See, basically, if you see the whole structure of all this, is that IBC has to control your IO cards. You need something with some amount of intelligence. So you need a microcontroller to basically see when the IBC sends out a command, something is required to receive the command and do accordingly. It is basically for communicating between the IBC. So it takes the data from IBC and then gives it onto your field. Otherwise, if you don't have a microcontroller, IBC just sends out the data and you have all 16 IO cards just sitting on the bus. The appropriate IO card should respond. For that, you need a microcontroller there. I hope I've answered that. Is it clear? Or, see that I think you can just talk with the HMI people because as I said, I am basically from the hardware side. So when we send out the module, we just send out the module blank. There is nothing on it. It's just the hardware. We make the hardware. And even the flash card is also blank when we send out the module from our department. All this is done again. All the programming of ACNCS is done by the HMI group, which you will be having a session later on. That's what I said. See, the other cards actually, all the other cards, see, all the cards need some field voltage for the field side circuitry to work. In the case of all the other cards, the 24 volt is taken from your mounting base on which your IBC and IPSP is mounted. However, for your digital input card and your frequency card, the 24 volt which powers the field side is taken from this connector which is mounted on the MBI8. So now here, if you give in a 24 volt, this 24 volt is also available for all the cards on this mounting base. So now if you are going to plug in your 48 volt digital input card, the 48 volt digital input card will need a 48 volt there. So the 24 volt will not suffice. So when you're mounting it, you can mount your digital 24 volt digital card and your frequency card on the same IO group. But you may not be able to mount the 48 volt digital input card along with your 24 volt digital input card, since the voltage required for both the cards is different. The 24 volt for your digital input card is given through this green connector here, yes. But the 24 volt for your other cards are taken from the, see if you pull out IBC and IPC, yeah, it depends on whether they're redundant, but that this will be covered in the afternoon. So obviously if it is non-redundant, you can't pull out the IBC. Okay. Okay then, thank you.
We request all the participants to enter their feedbacks, please. The format is given in the chat box. Kindly enter your feedback, then leave the site for lunch.
Can I leave the meeting?
Yes, madam.
And Madam Nirmala, you are able to listen me?
Yeah.
You are able to listen me?
Yeah, I can hear you, Padma.
Okay, okay. Thank you, Nirmala, for having taken the session so well. And I think our participants have got the maximum benefit out of it. Hardware, which is the real, the one our thoughts are put into and all that. So without hardware, software is nothing. So we thank you profoundly for having taken the session in a short notice. And we request you also to give away the slides to our staff who are present around you, Mr. Nagaraj or Swati, whomever you feel you can hand over it, so that we will be putting DHL file sharing system. And we also thank our participants for patient listening. And we will break for lunch now. Our next session starts at 3 p.m., which is analog modules. So far, we have learnt about digital modules and ACNs. Now, analog module session is there today at 3 p.m. We will all join at 3 p.m. Thank you. Thank you, Nirmala ma'am. Thank you, my dear HRD staff. You may come back for lunch also. Thank you.